Hello, math fans. Going to talk about the cross product here, and as we finish up our introduction to vector operations before we can head off into calculus and 3D. The vector operation today takes a little more work to compute than the previous vector operations, but it accomplished something very important. So in this video, I'll talk through how we compute it, conceptually what it is, how we make sure that we're right, which is very important. It's actually very fast to compute, and then I'll do a few visuals. I'll follow this up with what does the length of the vector mean, what in the world is this right-hand rule. There's several little side topics, but the main thing for us in our calculus course is being able to compute it. It accomplishes something very physical, meaning here are two vectors. These are the two vectors we're about to do the cross product of. If you were to pretend they're both from the origin like that, and you were to draw a plane that goes through them, this extended piece of paper that goes in all directions, it turns out that neither one of those vectors describes that plane individually. In fact, there's an infinite number of vectors that are parallel to that plane. The one thing that they all have in common is they're all perpendicular to the same thing. So when we go to describe planes or describe a surface, often one of the most important vectors is a vector that points straight out of both of those vectors. Now, how in the world do we find such a thing? And by straight out, I mean it's perpendicular to both of those. That's what the cross product does for us. Now, you can make the vector longer or shorter by rescaling it. The cross product just finds one such vector that does that. So that's what the cross product is. It gives a vector that's perpendicular to two vectors you started with. So it's very valuable in that way. Okay, so first let's just compute it. There's more than one way to do this. I used to teach it a different way. And then when I taught the courses that followed this, I realized I should teach you the determinate way of thinking about this, because that's what you're going to see if you leave this course. So anyways, here's what I do. And this is sort of to minimize space and check everything I can check. I put a little I here. I put a little J here. I put a little K here. And I form a 3x3 determinant. And you can see that I do this, since we do this so much, I try to be as efficient with my space as possible. I then tell students to set up their template. The template looks like this. And since it is a lot of little bits of arithmetic, you would like to have a way to check your work at the end, and we're going to have that. So cross product is really something we should almost never get wrong, and I'll explain why. So that's this I, J, K in the formula that I just wrote. Those are the parentheses I put. You have to write those things really anyways. So I just find that I immediately do the things I just did. I set up that template, and I find if students follow my advice, it works. The only weird thing, if you've never seen a 3x3 determinant, is that you have this negative here. So if you can just remember it's plus, minus, plus, that it alternates, then you're down to doing basically one multiplication at a time. And I have just found from years of watching students make mistakes on this, that the fewer things you can keep in your head, the better. And use pencil and paper. Okay, so here's how the technique goes, and then I'll show it down below. You cover this first row and first column up. You get this little 2x2 determinant is what we call it. It's okay if you aren't an expert on this, but the 2x2 determinant is very important in linear algebra. So you will see this at our university. It'll be Math 208. So eventually you'll know this well. So for me to teach you something else kind of is a distraction. So we're going to do, and also it takes more space, these other techniques that people use. So you do this number times this number, main diagonal minus off diagonal. So that's what we're going to do. We're going to do main diagonal 2 times 2 and write it here. And then we're going to do off diagonal 3 times 0 and put it here. And I really like that it's just, once I've set up my template, I'm all set. So then what do? We do it again. Except this is how you do 3x3 determinants and larger determinants. You cover up the first row and second column, and then we're going to do the same thing. Main diagonal minus off diagonal. So just a useful way to remember this. I'll say more about the history here in a second. So main diagonal 1 times 2 is 2. Off diagonal 0 times negative 1, 0. And then we do it one last time. Like I said, I also like that you can keep this in your head fairly quickly. Main diagonal, this times this, so 1 times 3. Off diagonal, -1 times 2, -2. And then I always do two things now. So then I simplify it, including distribute any negatives or whatever, and then I check. Now, how do I check? And this goes to the heart of what a cross product is. A cross product is perpendicular to the two vectors you started with. We have a really good way to check if vectors are perpendicular. We talked about that in the previous parts. You do the dot product. So you do two quick dot products. Now that part you can do in your head once you're good with dot products, but let's do it real quick. 4 times 1 is 4. 2 times negative 2 times 2 is -4. And 5 times 0 is 0. Since you know you're trying to get 0, you'll be able to tell right away if something's wrong. But anyways, 4 times -1 is -4. 2 times 3 is -6. 2 times 5 is 10. It's like satisfying. Then we know we're right. So it does indeed give a vector that's perpendicular. I don't know why I'm erasing that. To the two vectors, and then we're correct. So I do want to talk about a little bit of, and there's more to say, but I want to talk about reverse engineering this. Now, a brief detour, because the history is a little different than I expected. So I'm going to just say something. I'm going to pull from, so I'm not doing a careful review. This is just the summary from Wikipedia. This is this other technique where you basically write the matrix twice, but I do think that just takes more time. So it says in the 1800s, this was first discussed as part of something else. In 1881, they started using this notation to separate the dot and cross products. In a similar time, someone started calling it a scalar product and a vector product. So there you go. About, 150 years ago, is when these things started to play a role. So it's not that old, honestly. It actually says the first computations involved finding out how the standard basis vectors compute with each other when you do a cross product. And they did a big computation. And from that computation, they got this formula. That's a little different than how I've usually explained it. I like to give students a chance to try to reverse engineer this. But that's kind of interesting that that's how they did it. What I mean by reverse engineering is your goal is to come up with something that's perpendicular to the previous two vectors. So the real goal in this process, you could sort of think of it this way, is to come up with something, and you don't need to do this. I've given you the formula already. But come up with something that when you do the dot product with whatever formula you get, that's going to be 0, but at the same time, the dot product with the other vector is also going to be 0. So you could try to reverse engineer it. Now you could say, why can't we just use 0, 0, 0? Well, we don't want just 0, 0, 0. We want some vector. So the thought becomes you're going to need a bunch of cancellation. And you're going to do this times this, and this times this, and this times this. So you can already start to see what's going to have to happen. A few things that are going to have to happen. So I often tell students, if I gave you a start and gave you a little bit of time, you'd figure this out. It's not quite as mysterious as it seems. It's trying to accomplish a very particular goal. So if I set you the task of finding something that only involves the symbols A1 through A1, A2, A3, and B1, B2, B3. This should be B2, B3. Could you find something that works? And you'd immediately see that you have to have things cancel. And pretty much every term is going to have some sort of B in it and some sort of A in it in order to work in both. So often I tell students, well, what if I just gave you one of the terms and told you that this has to be A2, B3, and this has to be A2, B3, because they're the same. From there, you could figure out the rest. So what I mean about reverse engineering is you're going to have this times this. So if you expand the first one, you're going to have an A1, A2, B3. Somewhere along the line, you're going to have a minus A1, A2, B3. Where does that have to be? And you start to go, well, it's going to have to be where the A2 is to get this cancellation. So you go, well, maybe I need a minus A1, B3. And that accomplishes that, and those cancel. And you say, well, then this is the same. There's no guarantees when you first start to do this is going to work out. But you can see how you can sort of develop the formula. That is this term right here. Now, later, someone realized that this is exactly the same thing you get as the matrix, a 3x3 determinant. And so the reason it's written this way is it's to match up with how determinants are typically written. But you could then go, okay, that's good. Let's play the same game with B. If you expand this out, you're going to get A2, B1, B3. How am I going to cancel that off? Well, that's going to happen with the B3. So you're going to have a negative A2, B3. And when you expand that out, it's going to be A2, B1, B3, and those will cancel. So we figured out that, and that, and that, and that. So at this point, we've said, if you started with this, now that's the question, how would I know to start with this? But I gave you a starting point. You could actually pick some other starting point and see what happens, but this is the standard definition. We found out that this has to be there in order to cancel that off for the A, and that this has to be there in order to cancel things off for the B. Now, the moment you've plopped those things in there, you now only have a few places you don't know. And so then you play the game again. There's a few other combinations now we can use. For example, you could say negative A2, A3, B1 has to be in there. But that's going to have to cancel with something else. So it's going to have to cancel where the A2 is. So you're going to have an A3, B1 with a plus. So this is the sort of stuff I like to do. When I first taught this course, I was like, well, how could I convince myself of this? Well, I do a little reverse engineering. That means this has to be A3, B1, and now we have that. And hopefully you can kind of see the game. Now in class, I always stop there. But you could just keep going and saying, which ones have I not done yet? Well, I haven't done B, A3, B1, B2. Well, that's going to have to be over here because that's where the B1 is. So this is going to have to be minus A3, B2. And that means this has to be minus A. It's like I'm doing a game of Sudoku here is what it feels like. And then you keep going, and this has to be A1, B2, A1, B2. So it's really just trying to make the dot product 0. That was longer than I meant to take there, but I hope that was kind of interesting to show you that this isn't quite as mysterious as it seems. Okay. Historically, I guess that's not quite how it was done. It was done by thinking about first what the standard basis vectors cross products are, and then kind of deducing that. But there's another way to think about it. Okay. So that's really the concept, is that it accomplishes this very physical goal. It gives us a vector that points directly out of some plane. I think I'll leave it at that and talk about some other bits and pieces of it in a moment.